Hi everyone, this is Ramalinga Prasad Kuppa. Welcome to my channel, Pharma World. Today's topic is titrimetry as per USP chapter 541. In this video, we are going to learn on various types of classical titrimetric analysis. Titrimetric analysis are used for quantitative estimation of substances. It is essentially determining the volume of the solution of accurately known concentration which is required to react quantitatively with the solution of the substance being determined. Let us see what is titrimetry. Titrimetry is a technique used for estimation of compounds by using another standard by titration method. The accurately known concentration solution is called a standard solution. In this technique, the standard solution is filled in a calibrated apparatus which is called a burette. Smaller increments of about 0.1 ml can be added accurately from this apparatus. This procedure is called titration. The substance being determined is titrated. The process of titration ends when there is an equivalent point which is called an endpoint. In this technique, a soluble substance contained in a solution is estimated with another appropriate standard solution. So, accurately weighed amount of the substance being estimated will be dissolved in adequate amount of appropriate solvent and taken into a conical flask. Standard solution is taken in a burette. This is the basic setup of a titration method. Estimation procedures are either visual methods or instrumental methods. Equivalent point or endpoint is identified by a suitable indicator solution. Generally, the indicator solutions are colored and sharply change its color at the endpoint, in which color change can be identified very easily. Required amount of standard solution is added as a titrant from a calibrated instruments, a titrator or a burette into the solution containing the compound to be estimated. The selection of burette must consider that at least 30% of the titrant is consumed for achieving accurate titration results. This is a typical burette. Let us see what is a direct titration. Known volume of specific concentration of the titrate compound to be estimated is taken in a suitable vessel. Conical flasks are very useful and comfortable in carrying out titrations. Mixing will be uniform in such apparatus. Mixing can be achieved by simple swirling of the flask with your hand. The vessel could be a transparent, clean conical flask or another suitable apparatus that allows titration process to proceed. When titrations are carried out in a beaker, a magnetic stirrer arrangement may be made for mixing for reaction between the titrant and the substance to be estimated. This is a typical conical flask. Iodine flasks are used for iodometric determinations or any other compounds which are sensitive for decomposition when exposed to atmosphere. This also protects any possible vapors escaping from the open flask or open conical flask. Since the flasks are transparent silica glassware, color change of the indicator can be easily identified. The iodine flask typically looks like this. Endpoint is obtained by a suitable indicator for visual titration methods. As discussed in earlier slide, the endpoint is detected by a suitable colored indicator solution. The color change is identified by naked eye. Depending upon the type of titration, there are different kinds of indicators. They include acid-base, precipitation, complexometric, and redox, etc. So there are several types of indicators used for specific purpose. In acid-base titrations, pH sensitive indicators are used. These indicators have different colors at different pH levels. The change in color is also very sharp and easily identified. Typical indicators are methyl red, which changes from red to yellow when the pH jumps from a sharp range of 4.2 to 6.3. Phenolphthalein, which changes colorless to pink at pH between 8.3 and 10. In precipitation titration, the indicator adsorbs on the precipitate that forms during the titration. Typical precipitation titrations include estimation of chloride with silver nitrate solution. The indicators are used here are acid dyes or basic dyes. Generally, halides are estimated by this technique. Complexometric titrations are for estimation of metal ions such as zinc, magnesium, calcium, etc. EDTA is the best complexing agent. There are specific indicators for complexometric titrations. For example, iriochrome black tea is one of them. Redox titrations use the reduction and oxidation potential of the substance. Electrochemical measurements by potentiometric method are used to replace the requirement of indicator solution. This is useful if there is any possibility of human error in identifying the color change accurately. Electrochemical measurements are more accurate and less human errors. Let us see what is a residual titration. In such cases, measured volume of excess of the standard solution is added to the substance in solution to react completely. In direct titration method, the reaction between titrant and the substance to be determined is instant. In cases where the reaction between the reactant and the titrant is slow, the direct titration method is not suitable. It takes longer time for reaction. You need extended contact time. In such cases, the residual titration method works well. The contact time of titrant and reactant is longer. Excess titrant is estimated by another suitable standard solution. After the reaction is over, the leftover titrant is estimated by another standard solution. The amount of standard solution consumed by the titrate substance is estimated by the difference in volume of the blank titration and the sample titration. In residual titration method, a blank determination is carried out to estimate how much titrant reacted with the reactant. So the volume consumed for the blank minus the volume consumed for the test would give you the information on the volume reacted. This type of analysis is also called as back titration method. This is another terminology for residual titration method. Let's see what is a complexometric titration. In this type of titration, the metal ion that has to be estimated is complexed with complexing agent like EDTA. The most widely used complexometric reagent titrants are ethylene diamine tetraestic acid and the dihydrate salt of the sodium salt. Metals including zinc, cadmium, mercury, aluminium, magnesium, calcium, nickel, copper are accurately determined by complexometric method of titrimetry. In this method also, when the analytical reaction is not rapid, residual titration method can be adopted. Many of the complexometric titrations are carried out by residual method. It helps for complex formation completely. Chelation, ion exchange, precipitation are included in other types of complexometric estimations. Although there are several complexing agents, the most suitable complexing agents are EDTA and dihydrate of sodium salt of EDTA. Let us see what is redox titration. Oxidation process involves loss of electrons and reduction process involves gain of electrons. In redox titration process, a reducing substance is estimated by titration with an oxidizing substance, or an oxidizing substance is estimated by titration with a reducing standard. List of powerful oxidizing agents include potassium permanganate, potassium dichromate, ferric sulfate, etc. List of powerful reducing agents include titanous chloride, stannous chloride, and mercurous nitrate. This is another type of technique. It involves reduction and oxidation potentials as the basis for estimation. The endpoint is determined by visual titration method or electronically. It is similar to the procedure as described for the earlier titrations on acid base or other titrations. You can do either visual method or electronically. Typical indicators include nitrophenanthroline, 110 phenanthroline iron 2, diphenylamine, sodium orthocresol iodophenols, and methylene blue. These are typical indicators used for redox titrations. Let us see non-aqueous titration. Certain acids like acetic acid, perchloric acid behave as weak acids when dissolved in water, whereas they behave as strong acids in ethylene diamine, that is non-aqueous base. Weak acids and weak bases do not completely ionize in water due to their less tendency to ionize. Hence, for complete ionization of weak acid and base, we need non-aqueous solvents. This technique is very useful for assaying pharmaceutical compounds. Also, it provides suitable solvent for dissolution of many organic compounds. Perchloric acid and acetic acid are most used non-aqueous solvents. The endpoint determination also will be very precise. Many water insoluble compounds acquire strong acidic or basic properties in non-aqueous medium and can be estimated by non-aqueous methods. This is precisely the reason for adopting non-aqueous titrations. Also, physiologically active part of the moiety can be estimated more accurately in non-aqueous method by proper selection of solvent and titrant. So, specific moieties can be estimated very accurately by this non-aqueous titration method. Let us see how potentiometric titration works. Simplest and convenient way of identifying the endpoint is by usage of indicator solution. In visual methodologies, your eye is the detector to catch the endpoint. Since there will be a clear color change, the naked eye can detect the completion of titration easily without much effort. Potentiometry is another method. Potential difference between the reference electrode and the indicator electrode are utilized to get the equivalence point, that is the endpoint. Potentiometry is instrumental technique where the endpoint is detected by a sharp change in potential difference in the electrode assembly. The potential difference data is plotted as a graph and the data is presented as a sigmoid curve. The sigmoid graph looks like this. The endpoint is the midpoint of the sharp rise in potential difference. This plot is potential difference versus volume consumed. See this typical data. Let us see how the first derivative graph and the second derivative graph can be plotted. In this, difference in volume consumed versus difference in pH in this plot is plotted. 19.6 ml minus 19.5 ml is equal to 0.1 ml. Difference of pH value is 6.59 minus 6.46, which is 0.13. The ratio of pH difference and volume difference is 0.13 divided by 0.1, which is 1.3. You can see the same type of calculation is done in all other data points also. If you plot the difference of data of volume, that is delta V, and the difference of pH value, that is delta pH, you get the first derivative graph. The advantage of this graph is that the endpoint can be easily found. You can see the example graph in the next slide. In another type of graph, a second derivative graph, the difference of delta pH and delta volume is plotted. Delta pH is difference between 1.3 and 1.4, which is 0.1, and delta volume is difference between 19.5 and 19.6, which is 0.1. So 0.1 of delta pH and 0.1 of delta V is equal to 1. 0.1 divided by 1, that becomes 1. You can see this graph also in the next slide. Let us see how the first derivative and second derivative curves are better than the sigmoid graphs. The sigmoid curve, that is straight, the curve between pH and volume, looks like this. In the sigmoid graph, the endpoint is difficult to identify. In the first derivative curve, delta pH by delta V, you get a sharp endpoint. In the second derivative curve, that is delta second pH and delta second volume, you get again a curve like this. In this also the endpoint detection is easy. Sharpness of the endpoint detection is better than sigmoid graph in both first derivative and second derivative curves. Let us see other important points to note. The burette in which the titrant is taken should be between 30% and 100% of the rated capacity of the burette. This is important point to note. Volume consumed for titration must be within this range of 30% and 100%. That means if you select a burette of 50 ml capacity, the titration should be at least consume 30% of 50 ml, that is 15 ml. So the titrant volume consumed for the titration must be above 15 ml and up to any volume of 50 ml. When the volume consumed is less than 10 ml, the burette selected for titration should be of 10 ml capacity. Also, the least count should be 0.05 ml for such burettes. Least count is minimum readability of the burette. The volume delivered at the end of the titration should be in increments of 0.1 or 0.05 ml only. This is another important point to note. It is always recommended that at the near end point, the volume added should be in least count volume. It is mostly 0.1 ml for 50 ml burette and 0.05 ml for 10 ml burette. For certain dragging endpoints, it is necessary to add the indicator solution at the time closer to the completion of titration. Particularly when you are carrying out iodometric titrations, the starch indicator must be added only when the titrated substance turns light brown color. Then for the endpoint, a sharp change from blue to colorless can be achieved easily. If you are adding the starch iodine solution in the beginning itself, the endpoint will be much more dragging. I hope that the information in this video takes you through basics of titrimetry. Use USP 541 for more intricate details. Thanks for watching. For more videos, please do subscribe, like and share. Thank you.